Welcome back. We now begin the second part of this tutorial. First, we shall present strategies for efficient learning and sampling of energy-based models. The first method is a multi-stage coarse-to-fine expanding and sampling method. Suppose we want to learn an energy-based model. So in the training stage, we incrementally grow the energy-based model from a low resolution or a coarse model to a high resolution or a fine model by gradually adding new layers to the energy function. So each time we add new layer. And then in the testing stage, we just keep the learned models and we use short-run MCMC, for example, long-run dynamics, to sample the images at the highest resolution eventually. And this method proved to be very effective for generating very realistic images. This slide shows some result. So the figure on the left shows the MCMC generative sequence after learning the model on SLB-A data, where we use 50 long-run steps to generate the images. And the figure on the right shows the generated examples after learning the model on the SLB-A high-quality data at 500 by 500 resolution. So you can see that the generated images are very realistic. Next, we present a related method. This method is a multi-grid modeling and sampling method where we learn multiple models at multiple resolutions or multiple grids. And when we sample a model at a higher resolution, we always initialize the finite step MCMC sampling from images sampled from the models learned at lower resolutions. And of course, the lowest resolution is 1 by 1, where the model is simply the histogram. So the sampling process starts from this 1 by 1, the lowest resolution, and then we keep using finite step MCMC to sample the current resolution, initializing from the previous resolution. So this way, we generate images at multiple resolutions and multiple grids. And then we can learn the models at multiple grids. So this shows you some examples where we generate face images at bigger and bigger resolution. This slide shows some examples. So the figure on the left shows some images generated from the learned model after learning from Cypher dataset. And the figure on the right shows some examples of inpainting, where the first image is the original image. The second image is a masked image, where some of the pixels are masked so that they are not observable. And the third image is a recovered image. We still use the same sampling method to generate or to recover the image, except that in the sampling process, we always fix the observed pixels at their original observed values. And you can see that the MC sampling at multiple grids according to multiple models can enable us to recover the masked pixels. And the last example is a numerical example where we show that this method can be used for semi-supervised learning. So as we discussed in the first part, the energy-based model can be considered a generative classifier. However, we can learn the bottom-up network from unlabeled data. And after learning this model, this energy function, we can then use the top few layers as features. And then when we want to learn from the labeled data, we only need to grow a small network on top of those layers. So this enables us to learn from small amount of labeled data after pre-training on very big unlabeled data. So this method proved to be very effective for semi-supervised learning. We now introduce the third method. The third method is a diffusion-based modeling and sampling method. It is actually similar to the previous two methods, except that instead of creating images at multiple resolutions or multiple grids, we actually keep adding noises, the Gaussian noises, to the image in a diffusion process. So by adding more and more noise, we eventually arrive at a white noise image. So at time step t, say xt, is obtained by adding Gaussian noise of variance sigma squared to the image at the time step t minus 1. So this process, if you repeat it, it is a diffusion process, eventually leads you to a white noise image. So this is this q xt given xt minus 1. So this is a very simple diffusion process. And what we want is to learn the energy-based model for the images at all those noise levels corresponding to all those time steps. So the model is parameterized by a single network, which is a function of both x and t. So here we can use a certain vector embedding of t so that all those models are parameterized by a single network. Of course, it's still very difficult to learn those energy-based models marginally. However, we can learn, or we can first translate this energy-based model into a conditional version. So that is, if we consider the conditional distribution of xt minus 1 given xt, so that is, given xt, we want to recover xt minus 1, where xt is a noisy version of xt minus 1. And this distribution can be considered as a prior distribution of xt minus 1. And then we add this data likelihood, right? So which is a least square term, so that the marginal distribution continues to be a energy-based model with this energy function. And you can see that because of the regularization of this term, so given xt, this term requires that xt minus 1 to be close to xt if sigma square is small. So therefore, even though the original energy function may be highly multimodal, with this regularization, it is actually quite close to unimodal around xt, and the sampling become very easy. So it is just sampling from a conditional distribution which is close to unimodal. And this is actually a matter for denoising, or you can think of this as recalling xt minus 1, where we gave xt as a hint so that it is much easier to sample from than sampling from the marginal distribution. Okay, so after sampling images from this conditional distribution, where this xt is given as a noisy version of x0, you just add a certain amount of noise to the original clean image. And then you can learn the models at multiple noise levels or multiple time steps by using the same method, analysis by synthesis method. And then you learn this F network. So you learn the marginal models at all the noise levels. And then in the generation process, after learning these models, you can start from this noise, white noise image. And then you repeatedly sampling from this conditional distribution. Okay, so sample from those conditional distribution. Eventually, you will generate the clean image. So this is a reverse for this diffusion process, aided by the energy-based model. And in this process, we learn energy-based models at multiple noise levels. So it is very similar to multi-grid method, except that we don't learn at multiple grids or multiple resolutions, but we learn the model at multiple noise levels. So we call this method the diffusion recovery likelihood method. And these figures show some examples generated by the learned models. And you can see that they are actually very realistic at high resolution. And in terms of the FID score and the inception score, so this method achieves the best synthesis performance or synthesis quality among all the energy-based models. And here are some examples of imprinting, where the first row shows the masked images, and the second row shows the recovered images, and they are quite realistic. We now move to the second part, where we incorporate a generator network. So we treat the generator model as an approximate sampler for the energy-based model. So a generator model is actually a top-down model, where we always consider the observed example, for example, image at the bottom. And then this image X is generated by a hidden vector Z, a low-dimensional hidden vector Z, through a top-down network. So Z at the top and X at the bottom, and Z generate X through this top-down network G of theta. Okay, so this is G is a top-down mapping. So this is the structure for the generator model. And if we consider the energy-based model, the energy-based model is parameterized by a bottom-up mapping or a bottom-up network, where again, the image or the example X is at the bottom, and then we use a bottom-up network to compute the energy function, the negative f theta of X. Okay, so this is the form for the energy-based model. So for the energy-based model, you only need to specify a scalar function. So this f is a scalar function. Okay, but this g is a vector value function. It needs to produce this high-dimensional x. So therefore, it is much easier to specify or to learn this scalar function. And we can think of this f as an objective function, or the negative f to be the cos function, and f can also be considered as a value function. And you can think of this as a critic or teacher, as I will show you later. So as I mentioned, this energy function is easy to specify and easy to learn. However, we know that it is very difficult to sample fair samples, examples from the energy-based model. And because we specify this f directly, so it is a explicit approximation to the data density, and oftentimes it gives us a very strong approximation to the data density. And back to the generator model, it is specified by a top-down network. And as I mentioned, it is a vector-valued function. And you can think of this as an approximate sampler of the energy-based model, which is how we use the generator network. And in the language of reinforcement learning, you can even call this as a policy network, as compared to the energy function, which can be related to the value network. And you can also call it as an actor or a student. And the advantage of this generator model is that you can generate the synthesized images directly by this ancestral sampling. You just sample Z from a very simple prior distribution, and then feed Z to this top-down network to generate your X. However, this model only gives you an implicit marginal density. The marginal density involves intractable integral. And this model follows the so-called manifold principle, which assumes that the data lie very close to a low-dimensional manifold, maybe plus some Gaussian additive Gaussian white noise. But this model may not be a very strong approximation to the data density, may not approximate the density as well as the energy-based model. And these two diagrams illustrate the ideas of learning the two models. For the energy-based model, in our past work, we call this a descriptor as in comparison to this generator. So we just use EBM, but this is where we get D1 and D2. So you have inner loop, you use the long-term dynamics to generate synthesized examples. And then by comparing the synthesis examples to the observed examples, you update the model parameters so that eventually they match in terms of statistical properties. And in learning the generator model, you also need an inner loop to infer the latent factors in this hidden vector Z. And you can use long-term dynamics for posterior sampling. And after you infer this hidden Z, you can then learn this top-down network as a matter of least square regression. That is, you want to let G to generate or to be close to the observed examples given or by transforming this inferred hidden vector Z. More specifically, I guess most of you are already very familiar with the form of the generative model. So we have this latent vector Z follow a uniform distribution or a normal isotropic normal distribution, Gaussian distribution with mean 0 and identity variance cross matrix. So that is all the elements of Z are just IAD standard normal random variables. And then X is generated by G of theta of Z, which is a top-down mapping, and plus additive Gaussian white noise. Okay, and as I mentioned, this model actually follows this manifold principle where the high-dimensional data is generated by a low-dimensional representation. And this Z can also be considered as an embedding of this high-dimensional X. So we embed this observed X into a low-dimensional Euclidean space where we can do simple linear interpolation or some simple arithmetic in this latent space. And then after that, this can generate very interesting properties, nonlinear interpolation in the high-dimensional data space. This slide shows some important quantities. For example, this generative model actually defines a conditional distribution of X given Z, which is just a normal distribution with mean G theta of Z, and with a very simple variance cross matrix, sigma square identity. And often we just assume sigma square to be a tuning parameter. And the theta parameterizes the top-down network. And then given the prior and the conditional, we can get this joint. The joint distribution of X and latent Z is just factorized as a prior for Z times the conditional of X given Z. And in the more detailed form, it is like this form. So this comes from this term, the least square term, right? And this is like the prior distribution. We assume it follows a normal prior distribution. And then the marginal distribution can be obtained by integration of this joint distribution, where we need to integrate out this latent Z. So that's why this marginal distribution is in general implicit and intractable. So this is very much unlike the energy-based model, where we have a explicit unnormalized density function. But here, the marginal density actually involves this intractable integral. And then given X, we can infer Z based on the posterior distribution, which is the joint divided by marginal, and which is also intractable because the marginal distribution is intractable. Okay, now let us go over some technical details for maximum likelihood learning for the generative model. So first, we write down the log likelihood for a set of observations, xi, where I goes from 1 to n. We have n observations. And then the log likelihood is just average for the log likelihood for each observation. But here, this is a marginal distribution because we only observe xi. We don't observe the underlying zi. So we have to use the marginal distribution for the log likelihood function. And then for each generic x, then the derivative of log p theta x, this marginal density, will be just 1 over this p theta x according to the chain rule, and then multiplied by the derivative of this density, the marginal density, which is the integral for the joint density, where we integrate out the latent z. And then we can move this derivative inside. And then we use a very commonly used trick, which also underlies the reinforced algorithm for policy gradient. That is, the derivative for the density can be written as the derivative of the gradient of the log density multiplied by the density itself. Okay, and sometimes we also call this as the score, the gradient of the log density as a score function. And then we can move this p theta x, this marginal inside, because this is integral for z. And then we get this joint divided by the marginal, which is the conditional distribution of z given x, which is also the posterior distribution of z given x, which serve as the basis for us to infer z based on x. And then we continue to have this score function, the derivative of the log density. Okay, and then you can write this as expectation for this score function with respect to the posterior distribution. And then the expectation can be approximated by Markov-Chain Monte Carlo. So after deriving the gradient for the log likelihood, we can then use a gradient ascent algorithm for learning this data. And you can see that when you compute this gradient, first you need to draw samples from this posterior distribution, that is inferring z given this x. And this can be accomplished by, again, Langevin dynamics, where you have this gradient ascent step. So that is, you compute the gradient of this log posterior with respect to z, and then you add this Brownian motion or a diffusion term. Okay, so then after a number of steps, you draw samples from this posterior distribution. So the gradient for this log posterior with respect to z is actually the same as a gradient for this log of the joint density with respect to z, because they only differ by this log of p theta x, which has nothing to do with z. Okay, so this is a form for the joint density, the log of the joint density. Okay, so that is, you compute the gradient of the log joint density with respect to z in the Langevin sampling for inferring z. After you infer z, then you can just plug in the infer z and then compute the gradient of this log joint density with respect to theta for learning. So that's how you update the parameters. Okay, and therefore you can think of this algorithm, the learning algorithm, as alternating back propagation algorithm. So you compute the gradient for this function with respect to z in this inner loop for sampling z, and then you compute the gradient for this joint density with respect to theta when you want to update the parameter. Okay, so the inner loop involves this Langevin sampling, which is affordable, but still it can be time-consuming. So with the above preparation, we are now ready to present the cooperative learning method so that we can learn both the generator and the energy-based model in a cooperative way. So the generator model, we denote this as a p of theta x, where we use theta to denote the parameters for this top-down mapping. Okay, and it is a implicit integral, right? So the marginal density is the integral of the joint density, so that it is implicit. And we denote our energy-based model this time by pi of alpha, because we already use p of theta for the generator model, the top-down generator model. So the bottom-up energy-based model, we now use the notation pi of alpha. So alpha collects all the parameters of this bottom-up network that defines the energy function f of alpha x. Okay, so this is our current negative energy function, and z of alpha again is a normalizing constant. So we want to learn this generator model p theta and the EBM pi alpha in a cooperative way, so that they help each other. So both can be considered as an approximation to the data density p data. So here we use p data to denote the data density, and we observe samples from the p data. So this slide presents the basic idea for cooperative learning. And we do this with a so-called MCMC teaching method. Again, we have a top-down generative model, P theta, and then we have bottom-up energy-based model, pi of alpha. Okay, so we learn the two models cooperatively in the following sense. So first, we generate Zi hat from the prior distribution of the generative model, just Gaussian by noise, right? This is a noise vector. And then we use the current theta and G of theta to transform this latent vector to a synthesized image. Okay, so this is image generated by the generative model. And then we treat the generative model as an approximate sampler of the EBM. So therefore, we run a finite number of long-driven dynamics towards this EBM, pi alpha, under the current parameter. So you can think of this xi tutor as a revision for this xi hat generated by the generator. So that is, the generator is like a student, and EBM is like a teacher. So a student writes the initial draft of the paper, and then the teacher then revises the paper to get to this xi tutor. So this is considered as the synthesis example from the energy-based model. And then using the synthesis examples, we can then compare them with observed examples to update the parameter alpha for the EBM, right? But then how do we update this generative model? Well, you can see that this xi hat is the original draft generated by the generative model. And then it is corrected or refined by the EBM to xi tilde. So originally, this Zi hat, the generated latent code or the noise vector, reconstruct xi hat, right? Now we update our parameter from theta t to theta t plus 1 so that this Zi hat now reconstruct this xi tilde, the revised example. So this way, we actually distill this long-driven dynamics, this finite step long-driven dynamics into the generator model. So the generator model learns from the revision made by the EBM. So what's the advantage of this learning method? The reason is that this Zi hat is known. So in this generation scheme, so for this xi hat and xi tilde, we actually know Zi hat. Okay, so we just let the known Zi hat to reconstruct xi tilde instead of xi hat, so that we can refine or improve the generator model. So this way, we don't need the long-driven dynamics to infer this latent Zi, because we know this Zi. Of course, after you update this xi, the underlying Zi may also change. So if you want, you can also run a long-driven dynamics to further refine Zi to Zi tilde. Okay, so this way, then you can learn this theta so that this Zi tilde reconstruct this xi tilde. So this is a more rigorous scheme for this cooperative learning. So what we call MCMC teaching is that we use this short-run MCMC for refinement to teach the generator network. So that is the EBM as a teacher refines the initial draft of the generator, and then the generator learns from the refinement by updating its parameter to absorb the refinement. So you can think of from xi hat to xi tilde, this refinement process, as a tempo difference process, because you run some steps of long-driven dynamics according to the EBM, right? So you can think of this also as a tempo difference learning method. Okay, and as I mentioned, this Zi hat can also be inferred more rigorously, but then this long-driven dynamics can be initialized from Zi hat, and Zi tilde will only be a very small perturbation for this Zi hat. Okay, so this diagram illustrates the basic idea of cooperative learning by MCMC teaching. So that is the generator generate the initial draft from the generated noise vector. Okay, and then the EBM then refine it to the revised synthesis examples. And then you compare the synthesis examples with the observed examples to update the EBM, just like how we learned the EBM before. And then here, you then use the generated latent vector and the refined example to update the generator so that the generator should absorb the refinement made by the EBM as a teacher. Okay, so this is a basic idea of cooperative learning, and we call this as a Coopnice algorithm. The theoretical underpinning of this learning algorithm is as follows. So the learning of the EBM actually follow a modified contrastive divergence. We know that in contrastive divergence, you run a finite step of MCMC from observed examples. But here, we run a finite step MCMC where we use this M to denote the transition kernel from the examples generated by the generator model instead of from the observed examples. So basically, we use the generator model to jumpstart the MCMC, or we use the generator model to amortize the MCMC sampling for the EBM. Okay, and then the learning of the EBM follow the gradient of this contrastive divergence. So the first Kell divergence defines the MLE, and we have a second Kell divergence in order to cancel this log Z term. Okay, and the learning of a generator is by the so-called MCMC teaching. So that is let P theta T be the marginal distribution of the generator model at current theta T, and then you run a few steps of MCMC towards the EBM, the current EBM. And after a few steps, you get to this distribution. And actually what you do is to project this distribution onto the manifold for the generator model. Okay, so you updated theta T plus 1, which is obtained by minimizing this Kell divergence. So as if the training data becomes a refinement for the generated data. So the learning by MCMC teaching is that the inference of the latent Z become very easy because you know what latent noise Z that you use, the noise vector Z that you use to generate the initial draft. Okay, so therefore the advantage of this cooperative learning is that the generator jumpstarts the sampling, MCMC sampling of the EBM. And the EBM actually help to refine or to improve the generator model. So that's the basic scheme of this cooperative learning. This slide shows some results. So here are some texture images generated by the learned model. Actually, we learn two models simultaneously. And here are some scene images generated by the learned models. And also this interpolation result by the learned generator. And also we can use the model for impending applications. We can further improve cooperative learning scheme by a variational version of MCMC teaching, where we learn a inference model very much like a VE. I will skip over the details except showing you some synthesis results. But I would like to conclude the presentation of cooperative learning with a comparison with GAN. So in GAN, you learn a generator. However, in cooperative learning, you learn both the generator and energy-based model so that there is a refinement process according to the learned energy-based model. So this often leads to visible improvement of the examples produced by the generator model. So this actual refinement process proved to be quite important. And this is the key difference between our method and the GAN method. We now move on to the next method that completely avoids MCMC. We call this method divergence triangle, where we don't use any MCMC. So it is a framework that integrates variational and adversarial learning. So the generator involves the variational autoencoder, where the encoder serves as an approximate inference model. And the energy-based model is learned by the so-called adversarial contrastive divergence. And then if we put these two together, we actually arrive a very elegant form of a divergence triangle that involves three equilateral divergences between three joint distributions. First, we recast the variational autoencoder for the generator learning from the perspective of equilateral divergence. So we treat this as a so-called divergence perturbation. So first, a little bit notation. So again, we have Pz as a prior for the noise vector, and then P theta x given z defined by the top-down generator network. And then this gives us the joint distribution of observed x and the latent code z. Okay, and we call the joint distribution as P. So it is parameterized by theta, which are the parameters in the top-down mapping, top-down network. Okay, and in the variational autoencoder, we also learn a inference model, which is often written as Q of phi for z given x. So this is in an explicit form, often assumed to be a Gaussian distribution. And this is approximation to the true posterior distribution of P of theta z given x, right? And then we also have the data density P data. So the expectation with respect to P data can always be approximated by average over observed examples, okay? And we have this P data of x, and then we pair it with this inference model Q phi z given x. So this gives us another joint distribution of x and z. In fact, x can be considered as observed data, and z as a missing data. So this inference model is like imputing the missing data, so that we have this Q parameterized by phi of the joint distribution of x and z. Okay, so this is another joint distribution. So in fact, if we look at VE, it can be considered as a joint minimization between this Q of phi and P of theta. So this is the data distribution, and this is the model distribution. However, this time, this is distribution of the so-called complete data, where x is observed and z is missing or hidden. Okay, and this joint chiral divergence is actually tractable, and this is actually a perturbation of the first chiral divergence from the data distribution, the marginal distribution of the data, and the marginal distribution of x according to the model. Okay, again, this is a data distribution and this model distribution, but both are marginal distributions, and this one is intractable. Okay, so therefore we add the chiral divergence between this conditional distribution, the two conditional distributions, so that we make them into the chiral divergence for the joint distributions. So that's what we call divergence perturbation. So this first divergence underlies maximum likelihood, okay, and it is intractable because the marginal density is implicit. But with this perturbation of this term, which is a very important term in variational inference, we change this chiral divergence between the marginals into the chiral divergence between the joints, okay, so that this becomes tractable. And then you can think of this VE as an alternating projection. So you have a Q family where each point is corresponding to a value of phi, right? And you also have this P family. So you do this alternating projection until convergence. So this is how we understand variational autoencoder from this divergence perturbation perspective. We now try to understand the joint training of energy-based model and the generative model, again, from the divergence perturbation perspective. And in fact, we can focus on this formula. So P data is a data distribution, and the pi alpha, again, is the density of energy-based model with the parameter alpha, because we use theta as a parameter for the generative model, P theta. Okay, so now if you look at this, this expression, so the first Child divergence is the Child divergence between data density and the density for EBM. So this is actually underlies the MLE, maximum likelihood learning for energy-based model. However, the log z term we know that involve intractable expectations that can be approximated by MCMC. Suppose we don't want to use MCMC, then we can use a generative model as a approximate sampler. And then we define the following adversarial learning, where again we minimize this Child divergence over alpha. So the minimizing the first Child divergence leads us to maximum likelihood. And then we subtract the second Child divergence, which serve as a perturbation, and this time a negative perturbation by the second Child divergence. And this negative sign actually underlies the adversarial learning. So this objective function actually can be more elegant than the original GAN objective. And in fact, it is closely related to Weierstrass GAN and also inverse reinforcement learning. So let's try to parse this formula more carefully. So you can see that actually this defines a chasing game in the sense that, so here, if we want to maximize this value function over theta, so this first part does not involve theta, right? So that means we need to minimize the second cubic divergence so that we want the perturbation to be as small as possible, or we want this P theta, the generator, to be as close to the energy-based model as possible. Okay, so that's the maximization part. And for the minimization, actually, this is a perturbation for this Child divergence underlies maximum likelihood learning of energy-based model. Okay, and the learning gradient for alpha actually is just like this, as if we sample the synthesis images from this generator instead of from the current energy-based model. So therefore, you can see that here the generator chase this energy-based model, but this energy-based model try to get close to this data density as compared to the generator density. So it is like a chasing. So this P theta, this generator chase the EBM, and the EBM actually runs towards the data density and runs away from the density of the generator. So that is this pi of alpha serve as a critic. It criticizes this P theta, the generator, against the data. Okay, so this is adversarial interpretation, which has a very clear chasing interpretation. Okay, probably it is more clear than the original GAN objective function, especially in this very simple form for contrastive divergence. Again, this is in the form of contrastive divergence, except that the synthesis examples are generated by this generator network. Okay, now we are ready to put adversarial learning and variational learning together by this divergent triangle. So it involves three joint distributions on Z and X. The first one is a Q distribution, which is a P data X times this inference model. The other is a P distribution, which is a generator model, the joint distribution of the generator model. The third one is the pi distribution, which is the energy-based model times this inference model. Actually, you can also replace this by a so-called latent energy-based model that define a density on both z and x. Okay, now we have these three joint densities on z and x, and then we can define the following divergent triangle, which is in this form, and then we either max or min over those three parameters. So this enables us to learn all these models simultaneously without MCMC. In particular, there's a VE element where this P and Q, they run towards each other. And then there's the adversarial contrastive divergence element where this P runs towards pi. You see, P chase pi, but the pi runs towards Q and runs away from this P. That's why we use this right arrow. So pi runs away from P, but the P chase pi towards this Q, the data distribution. So in this way, we can learn the energy-based model without MCMC because we use the generator as a approximate sampler. And also we can learn VE or generator model with a better synthesis because now the learning of the generator model is actually regularized by the EBM as the target density. So that is, this P has to be close to this target density defined by this energy-based model. Okay, so this gave us a unification or at least an integration for adversarial learning and variational learning. This slide shows some image generation results and also interpolation results in high resolution by this divergence triangle. We are now ready to move to the next part, which again involves a generator model. However, instead of learning a generator model and energy-based model separately, we now learn an energy-based model in the latent space for a generator model. We call the resulting model as the latent space energy-based prior model. So again, we let X be the observed example, for example, an image, and Z the latent vector. And again, Z generate X through a generator network defined by parameter beta. And then P0Z is the original prior model, for example, Gaussian white noise model or uniform model. But this time, we also learn a small network in the space of Z. So this F alpha Z parameterized by alpha is a neural network defined on Z. So because Z is low dimensional, so it can be a very small network. Okay, and then we assume that the prior model for the latent Z follow a exponential tilting of the original non-informative prior model. Okay, and then Z still generate X through this G, the generator top-down mapping. Okay, so therefore, now the energy-based model is defined on Z and it stands on a top-down generator. And in fact, the model P of alpha, the prior model is exponential tilting of the original non-informative prior. So this actually follows the so-called empirical base principle, where we can also learn the prior distribution from the data empirically. And because this Z is low dimensional, so this F alpha that defines the energy-based model can be a very small network, and yet it can lead to significant improvement in the model over the original generator model. We can continue to learn the model by maximum likelihood. So this is actually very similar to what we derived before. So the gradient for the log likelihood can be written as the expectation with respect to the posterior distribution of the gradient for the log joint density. And this time, the joint density can be decomposed as the prior and this conditional. right? The prior is parameterized by alpha, and the conditional is parameterized by beta. Okay, so this gradient follow the same derivations as we did before. So the learning gradient for the EBM prior distribution or prior model is like this. So it is similar to the previous learning method for the data space energy-based model. So the only difference is that here you see the learning gradient, this part, so the expectation is not for the observed X, because now this network is defined for latent Z. So for each observed X, we need to infer Z from its posterior distribution. Okay, and then this is the derivative of log Z term. Actually, it's just the expectation under the prior model. So this is like a data part, and this is like the model part. We want to match the model to the data. However, here, the data is actually the posterior distribution of Z given the observed X. And in fact, after learning, we actually match this prior distribution with the aggregated posterior distribution, averaged over all the observed X. And the learning of the generator is still the same as before. It's just a reconstruction. So after we infer this Z, we can then learn G to reconstruct X from this Z. And this arrow in the yellow color denote the conditional distribution of Z given X, which is the posterior distribution. So this is a learning and sampling algorithm. So you read in a mini batch, and then you do prior sampling from the prior distribution, and then you do posterior sampling from the posterior distribution. And then you learn the prior model by comparing the sample from the prior distribution and the samples from the posterior distribution. And then you learn the generation model by reconstruction. So the algorithm is very simple and also very efficient. And this type of model is actually quite powerful, and it has been applied to many different applications. For example, image generation, text generation, and molecule generation, either unconditional generation or conditional generation. And it can also be applied to trajectory prediction, where the energy function can be interpreted as a value function or cost function. And it can also be used for semi-supervised learning, where the concept of information bottleneck can be very naturally incorporated. So in part 3, you are going to see those applications. You can also annotate MC sampling from the prior distribution and the posterior distribution by learned approximate samplers or learned models. And again, you can do that within this divergence perturbation framework or divergence triangle framework. And again, the first divergence underlies the maximum likelihood learning, and then you perturb it positively by the second chiral divergence, which is between a approximate encoder or inference model, like in VE, and this true posterior distribution. Okay, so if you add this term, you actually get variational autoencoder. And in fact, variational autoencoder can still apply to this latent space energy-based model. You only need to incorporate this energy function, negative energy function. So that is this error indicating the conditional distribution of Z given X can be approximated by an inference model. And similarly, the sampling of the prior distribution can also be approximated by a model, for example, flow-based model, if you want. And then you can train both the original model and the approximated samplers by this objective function in the form of divergence triangle, where this positive perturbation actually corresponds to the positive phase, where you sample Z from the posterior distribution given observed X. That's why it's called positive phase. And then the negative perturbation actually corresponds to the negative phase, where you sample Z from the prior distribution. Okay, and in fact, you can also use this objective function and this theoretical framework to justify the use of short-run MCMC as an approximate sampler. And in fact, usually you can simply attach the posterior sampling because this actually need backpropagation through this top-down network. So it takes a little bit more time. For prior sampling, actually it is very simple because this F is a very small network in the latent space. So a persistent MCMC chain can be very efficiently implemented. So we don't actually need to attach the prior sampling. We only need to attach the posterior sampling by variational autoencoder, and a VE can still be generalized to this type of model. Here are some synthesis results and FID score. And in this slide, I will show you the generation by this short-run MCMC and also the long-run MCMC. So here we plot the energy. And you can see that even for the long-run MCMC, it still keep changing. That means it is not stuck in the local mode. And in fact, the MCMC in latent space mix very well. So therefore, the latent space seems to be a very natural home for the energy-based model, so that you can capture the regularities, constraints, or rules, or objectives, or cost, or values in the latent space very conveniently. We now move to the last part, which emphasizes discriminative learning without MCMC. We start from this noise contrastive estimation of EBM. So again, we want to learn such a energy-based model. This time we use a P of theta to denote the energy-based model, just like our Euro notation. And you can also write this as an exponential form where C is a log of Z. And according to this NCE method, noise contrastive estimation method, theta can actually be learned in contrast against a noise distribution Q. So this Q of X is a very simple distribution so that we can write down the normalized density in closed form. Okay, and then following the idea that EBM can be considered as a generative classifier, so we turn the learning of EBM into a discriminative or classification task, where we maximize the following objective function. Okay, so this is expectation with respect to P data. So this can be approximated by averaging over observed training examples. And this Q, so expectation with respect to Q, can be approximated by averaging over the generated examples from the noise distribution QX. So why we can use this J of theta? Actually, this is just the log likelihood of logistic regression in supervised learning. So very similar to GAN. So we use the Q of X to generate those faked examples. And then we learn P theta X to tell apart the faked examples and the real examples. So this is a logistic regression where we introduce the label y equals 1 if x is a training example and y equal to 0 if x is a generated example from the noise distribution. And then according to the Bayes rule, let's assume that the prior probabilities are the same. Then the conditional distribution of positive given x is this ratio, right? This ratio according to the Bayes rule. And therefore, the log likelihood for each observation xi will be log of this one for the positive examples and log of 1 minus its probability for the negative examples. So this is nothing but the log likelihood for the logistic regression. And so here again, Q of x is a normalized density function of the noise distribution, and the P theta is a normalized density of the energy-based model. So we assume that the data, the true data, real data can be approximated or approximately explained by this energy-based model. Okay, and this actually follow the discriminative perspective for energy-based model. Okay, and then how do we choose this noise distribution? Actually, we use the flow-based model. We don't need to get into the details of the flow-based model, except that it is a composition of a sequence of invertible transformations where the Jacobian can be explicitly computed. Okay, and therefore, this flow-based model gave us a explicit, normalized density function for the x. So that is z is the original noise, and then we use a sequence of transformations, and we let g of alpha to be the composition of the sequence of transformations, and then we get x. So z often assumed to be Gaussian white noise, and after this transformation, using the change of variable, we actually can obtain the density of x in a normalized version in a closed form. Okay, and we use this type of model as the noise model because it gave us a very good approximation to the data density. So if we compare energy-based model with flow-based model, the energy-based model has a free form. You can use whatever CNN or any network to parameterize the energy function, and it directly corresponds to a classifier. But the maximum likelihood learning can be very time-consuming because of MCMC sampling. Flow-based model gave us exact density in the normalized form, and it can generate examples by direct ancestral sampling, right? You sample Z as white noise and transform it into X. But unlike the generative model, so this transformation G of alpha is an invertible transformation. But because of the invertibility and also the explicit Jacobian, so those transformations are actually of a very contrived form. So you have to compose those very unnatural and carefully designed transformations. So it is not very flexible and not very expressive. So therefore, we can combine or train the two models jointly and using this objective function. Okay, and the choice of this Q, as I mentioned, is first it should be very simple and it has an analytically tractable normalized form, and we can easy to draw sample from, and hopefully it is close to the data distribution. So a flow-based model serves this purpose perfectly. And in fact, I'd like to emphasize that we can also replace the flow-based model by variational autoencoder, and it also satisfies analytical tractability in one approximately because there's a extra layer of approximation by this approximated inference model. But actually, again, we can use VE as our Q, the noise distribution. Okay. But here, let's focus on this flow contrastive estimation, where we use Q as our noise distribution, and then we continue to use the log likelihood of the logistic regression as our value function, and then we estimate or we learn theta, which is a parameter of the energy-based model, and alpha, which is a parameter of the flow-based model, jointly by this very similar to this GAN scheme, right? This is very much like a GAN, and later I will show you the difference. And by this min-max adversarial training, we actually can learn both the flow-based model and the energy-based model jointly. Okay, and for this energy-based model, actually it just follow noise contrastive estimation, where the noise distribution is this flow-based model. But the learning of the flow-based model actually is minimizing a so-called Jason-Shannon divergence from this Q alpha to the P data, assuming that the energy-based model to be a very good surrogate for the data density. So basically, we let energy-based model to be a surrogate of the data density to further improve or refine the learning of this flow-based model. So that's the basic idea of the joint training. But if we compare this scheme to GAN, in GAN we learn a discriminator, and the discriminator is actually based on this likelihood ratio, this one. Okay. However, in the flow contrastive estimation, because we know this Q, the density of this Q alpha, so the Q alpha is in explicit normalized form, we can actually also learn this P theta explicitly, so that we learn this energy function explicitly instead of just learning a ratio as in GAN, okay? Because we know the density of this Q, okay? And you can think of this Q as an actor or a policy in the language of reinforcement learning, and the P as a critic or value. So this is essence of flow contrastive estimation. And it can be used for image synthesis. In fact, it leads to a better synthesis that improve upon a flow-based model, because you have a energy function to further regularize the flow-based model, and it generates better FID scores than the flow-based model. More importantly, this method can also be used for semi-supervised learning. So that is for the unlabeled data, you can train both the flow-based model and the energy-based model jointly, where the energy-based model is trained in a discriminative way, like a classifier. So that is EBM is like a generative classifier, but it is learned from unlabeled data. So therefore, this method gives us a probabilistic generative framework for this contrastive self-supervised learning, which is a very popular topic. However, if we use NCE, noise contrastive estimation framework, actually we get a very rigorous probabilistic generative modeling method, so that we can unify both generative modeling and discriminative learning in this way. So this is the importance. So when you train a energy-based model, you are not training a generative model, you are also training a classifier, or at least a pre-training for a classifier that can be used for downstream classification tasks. This example shows that this method indeed leads to very good performance on semi-supervised learning.